Okay, the video we have from class on Tuesday. We lost the audio. I don't know for what reason or why, what was wrong. It could be in the microphone, could be in the, excuse me, I'm having to fool with this. Okay. Sorry. Okay. So, again, don't know if it was the camera, don't know if it was the docking station, don't think it was the computer, but I'm using the computer microphone to record this. So I don't know how well this is going to turn out. I've also got another microphone, independent voice recorder, that hopefully will pick things up well if the recorder on the, or the microphone on the computer doesn't. Okay. Anyhow, talking about chapter 3. Now, we started out with vector valued functions. And as soon as I wrote the heading vector valued functions, I wrote down a typical example of a vector valued function. It's a function actually of two variables, x and y, but that's not too difficult to understand. So this r vector is defined to be xy over x squared plus y squared times the I vector minus square root of 9 minus x squared minus y squared times the j vector. Now, I was actually kind of jumping the gun here because the chapter that we're trying to give you a heads up on is actually just vector valued functions of one variable. But since we started this, we went ahead with this until I realized that we really wanted to come back to one variable. Okay. So anyhow, we looked at the domain of this function. We didn't think too much about the range, but we could have. Okay, what's the domain of this function? Well, we have two restrictions. A denominator can't be 0, and you can't take the square root of a negative quantity. So that x squared plus y squared can't be 0, and 9 minus x squared minus y squared has to be greater than or equal to 0. Well, x squared plus y squared equals 0 has exactly one solution. You might think about what that is, but there it is. X equals 0, y equals 0. If x is anything but 0, then x squared is positive, so it's greater than 0. And y squared can't be negative, so that automatically you don't have a solution. If either one of these variables is not 0, there can be no solution. Okay, we have this inequality, which is easy to rearrange to x squared plus y squared less than or equal to 9. And we know from what we've been doing that x squared plus y squared equals 9 is just a circle of radius 9 centered at the origin. So that this is just the interior of a circle centered of radius 3 centered at the origin. So you could actually draw a picture of the domain. And I'll kind of do it over here, make sure that everything's visible. I think we're good. Circle of radius 3, it's a very bad circle. Take the interior of that circle, that satisfies this. But then we can't have the origin. Okay, so the origin has to be excluded. So we can kind of do that with an open dot around the origin. So it's everything in this disk of radius 3 except the origin. Now, that's kind of an important picture for stuff that you might encounter later on in this course and more likely in some other courses. Okay, in the range, well, we say the I component can approach 0. Okay, so this thing could approach 0. Now, it could be positive or negative. The denominator is always positive. But if x and y have the same sign, it's positive. If they have different signs, it's negative. But this can get arbitrarily close to 0. Okay, depending on how we approach the origin. Now, I just said that, and actually, you might want to think about that. I hadn't really thought about that statement, so I've got to think about it a little bit, but certainly, if x equals 0, then your numerator is going to be 0. And then if y doesn't equal 0, your numerator is still 0, but your denominator won't be. So you can certainly approach 0, and you can approach it through positive or negative numbers. Because if x is 0, then y could approach 0 through positive or negative numbers, meaning that you'd be approaching the origin along, well, either from the positive y-axis, approaching 0, or approaching 0 from the negative y-axis. Question, do we actually have a limit at x equals 0? Well, I can pretty easily prove, and I did, that we don't. If I approach along the line x equals y, then what do I have? X equals y, so this is like x squared. X equals y, so if I replace y with x, I get an x squared here. I've got an x squared here. I'm going to have an x squared over 2x squared. That's 1/2. What if I approach it along the line x equals negative y? Well, then I'm going to get like negative x squared over x squared. Okay. Which would give me negative 1/2. Our limit would be negative 1/2. We approach 0 along this line. The limit's 0 if we approach it this way or this way. Okay. So that we don't have a limit as x, y approaches 0, as we approach the open dot here. Now, often we will, depending on the kind of a function, but in this case, we don't. Now, I wrote this kind of sloppily. It says limit as x, y approaches 0. I can't even tell that arrow is there. Yes, that still can't. Of xy over x squared plus y squared does not exist. There's no such thing. Because, again, you get different answers if you approach from different directions. Okay, well, this is really chapter 4 stuff, first section of chapter 4. So store it away. It's kind of important stuff. And now we're going to bring it back into simply functions of one variable, vector functions of one variable. Now we say vector valued function. Let's be clear. The value of this function is a vector because it's a combination of I and j components. And we put an arrow over the R to indicate that it is a vector. And it is certainly a function, in this case, of x and y. Now, we could go to parameterization. If we let x equal t squared and y equals 2t, we can use the same function and get a function of one variable, a vector valued function, where we have only one variable. Okay. So if x equals t squared and y equals 2t, it's really easy to see that if we plug those values in for x and y, we get r of xy equals 2t cubed over t to the 4th plus 4t squared minus, well, I don't have to read it to you. There it is. You can check it yourself. Okay, in that case, well, what is dr dt equal? What is the derivative of this function? We take the derivative of this function. Well, there's formal arguments. There are formal arguments to say that the derivative must exist if these functions are both differentiable, and it's not hard to prove that. So it seems so obvious that we're just going to, for now, assume that it's obvious. We'll get a little more rigorous as we go further into the course. Okay, so we have dr dt equals whatever. You can calculate this derivative, and it's if you have time, I recommend it. A good little refresher. You got to use a chain rule over here, and you got to use the quotient rule over here. And it's a little bit messy, okay? You're going to end up with a square root of this whole thing in a denominator and a numerator, and that's for your j. And here you're going to end up still with a numerator and denominator. I will note that unless t equals 0, and in the case, well, unless t equals 0, this can be simplified, right? You can just divide out a t squared from the denominator and the numerator. So it could get a lot simpler than it looks. Okay, well, anyhow, you can take the derivative with respect to t. Now, if t is interpreted as time, then dr dt be interpreted as a velocity, rate of change of position. In that case, we could take a derivative of the velocity, we get the acceleration. And we're getting up to a real important picture here, but the derivative of the velocity would be the acceleration. Well, that would be the derivative of dr dt, which would be the second derivative of r with respect to t. Okay. And if you want to take the second derivative of this function with respect to t, well, it's going to get pretty messy. Again, that would be good for you to do that derivative if you have time and want to stretch yourself a little bit, because most people coming out of first year calculus aren't as adept with derivatives as they will be when they get out of this course. Okay. Be a good transition. And there's nothing difficult about taking derivatives. It just can get messy. You just got to keep track of things. You've only got a few rules, and just follow them and then check yourself. Okay, well, if we now consider this dr dt as being a velocity, or if we use b to stand for dr dt, then first of all, dr dt is in the direction of motion for moving along a path. Okay, I should stop and say, and we should be kind of familiar with this by this point, that this function r of t will describe a path in this case in two-dimensional space. If we had a k component on there, then we'd have a path in three-dimensional space. If this function is differentiable everywhere, as is the case here, except perhaps at t equals 0, well, we could have a restriction because this too. Let's not get into that though. Then this velocity will be in our direction of motion. Okay. The derivative of r with respect to t will be in our direction of motion. There are a lot of ways to understand that. And in the earlier introduction in this course, you dealt with some of those questions. Okay, so the vector v is tangent to our path. So if our path is like this, now it's kind of wavy there, but let's just take a point like right here. Okay, there's the like our dr dt at this particular instant. I can't seem to make a good X. Okay. If we're driving a car, driving along a curve, maybe we're driving along a curve that's going up the side of a mountain, and we're moving in 3 dimensions. At any instant, we're moving in some direction, and that direction is the derivative of the vector function that describes our position as a function of time. There's a unit vector in our direction of motion, which would just be the v vector divided by its magnitude. Or if you prefer, the dr dt vector divided by its magnitude, called the unit tangent. Now, I'm going to say that we have an acceleration. Unless we're moving along a straight line at constant speed, we're going to have an acceleration. If we change our direction changes from this way to this way over some short time, then our direction has changed well, if our velocity vector changes from this to this, then the vector from the tip of this vector to the tip of this vector is our change in velocity. Okay. And that's because this plus this equals this. Therefore, this minus this equals this. and this minus this is the change in the vector. Now, second vector could be longer or shorter than the first. Our change doesn't necessarily have to be sort of in a perpendicular direction with our original vector. It could be out this way or back this way. If we're moving at constant speed, though, we form an isosceles triangle. We take limits as our time interval approaches zero, and we find that the vector here in the limit will be perpendicular to our velocity. And that would be, well, that vector divided by the time interval limiting value thereof would be our acceleration. Okay. And that would be, in the case of a constant velocity, is a tripetal acceleration. For the center of whatever circle it is, we happen to be temporarily moving along. And I can take this picture again. See if I can smooth out this curve a little bit. I could draw a circle right here. And that's an approximate circle that almost completely matches the curve for a very short interval before and after this point. Okay. It's called an osculating curve. We'll talk a little bit more about that. My point is that since our motion then would be indistinguishable to motion around this circle, then we would certainly have a centripetal component of that motion. Okay. So what I'm saying then is that our acceleration, which would be the derivative of velocity with respect to time, will have a tangential component, a scalar tangential component in that case. It turns out that that scalar, well, that tangential component can just be calculated by taking the dot product of A with our unit tangent vector. Okay. B over magnitude of V is our unit tangent. So A dot B over magnitude of B would be A dotted with the unit tangent. And we should know by this point that if we dot a vector with a unit vector, we're getting the component of that vector in the direction of the unit vector. Okay. So we could call this the unit tangent, and we will in a minute. And I'll go ahead and say, okay, unit tangent T. So that this calculation here would be A dot T equals A dot B over magnitude of V. Okay. Go to this picture. So you can see this slight curve here. You can imagine a circle that matches this curve, that fits this curve as best it possibly could at this point right here. Okay, so that circle might be out here somewhere. We have a velocity that we can easily calculate if we know our R of t function and if it's differentiable. So there's our velocity. Here's our unit tangent. If the velocity is greater than 1, okay, our unit tangent might be shorter than the velocity. Of course, the unit tangent and the velocity might be depicted on even completely different scales, but let's not worry about that right now. Okay. Making sure that everything is showing up on the screen. Okay, so here's our unit tangent. Here's our velocity vector. Here's our acceleration vector. We're going to assume an acceleration. We're going around this curve, so we do have a centripetal acceleration, an acceleration perpendicular to our tangent vector. But in this case, we're also speeding up, so we have an acceleration in this direction, gives us a net acceleration vector like here. We project that acceleration vector back on the direction of our velocity or our unit tangent vector, and we get the parallel component of the acceleration, the component of acceleration parallel to our direction of motion. Okay, and that's this vector. We also have the acceleration here. Okay, this parallel component of the acceleration can be calculated just by doing A dot T. Another way, yeah, okay, never mind. Okay, so there it is. We do A dot T. Now, we also have a perpendicular component of acceleration, and that's what we would get if we projected the acceleration on a vector perpendicular or on a direction or vector perpendicular to our velocity vector. We could easily calculate that vector if we know the parallel component and the acceleration vector, and we just subtract the parallel component from the acceleration vector or add a negative parallel component to the acceleration vector. And that gives us our acceleration perpendicular to the direction of motion. So we have a parallel and a perpendicular component of acceleration. We have, of course, our unit tangent vector. We're going to want a unit normal vector. To get a unit normal vector, we just take the perpendicular component of the acceleration vector and divide by its magnitude, and there's our unit normal. So T, big T, and big N are unit vectors, unit tangent, and unit normal. I'll mention that there's another way to get the normal vector. This direction is theta. Sorry, if this angle here between our direction of motion, our acceleration vector is theta, then we take the magnitude of A times the sine of theta, and we get the magnitude of our perpendicular vector, okay? And so we can use the cross product because it involves a sign and so forth. And I think your text has a formula that's good to deconstruct and understand, okay? For calculating this. There are various ways of calculating this, but we want to understand this picture, very important picture. Okay. Now, if we're three dimensions, there's a binormal vector. Okay, imagine we're driving up a curving mountain road and the road is banked in various ways. So, we're driving along and we curve around this way and we bank this way and then we turn and bank this way, or maybe it's banked this way and we turn this way. Okay, we can imagine our vehicle being accompanied by three vectors. One in our direction of motion, one perpendicular to our direction of motion, and those vectors are going to change. As a matter of fact, if we're going to round a curve to the left, our normal vector might be this way. And we go around to the right, and all of a sudden it switches this way. Our unit tangent vector is always what we regard as straight ahead. Now there's a vector perpendicular to those two that you could find by taking their cross product, because these two vectors are perpendicular and they're in the plane of motion. So, if we're banking a little bit, our plane of motion is going to change. So we do a cross product. And there it is, my thumb. And when we bank, that cross product changes. If we go uphill or downhill, that thing changes, okay? That's called our binormal vector. Binormal N dot T, cross T, okay? We just take the cross product of our normal and our unit tangent. And we do the normal cross the tangent vector, the normal, the normal vector cross the tangent vector. That's what we're going to define to be our binormal vector. Okay, and it's kind of a neat idea. Now, next time we're in or surrounded by mountainous terrain here, you do have opportunities to go up and down mountains and hills, or go up Route 80 over near the Great Channels. Neat experience. don't think about it too hard while you're driving because, you know, you don't want to be distracted. But think about it after you've driven. You imagine what these vectors might look like. If you happen to be a pilot, of course, flying a plane, all kinds of interesting things happen. But again, you probably don't want to distract yourself with it while you're trying to operate the aircraft, especially if you're doing a lot of maneuvers. I wouldn't know, I'm not a pilot, never, never driven a plane. Okay, so what are we saying here? Okay, so we've got the binormal vector, and of course, any vector is going to have components and direction cosines with your normal, tangent, and binormal vectors, all that stuff. Again, you know, what we're doing here is just giving you just an overview of the things that we do in chapter 3. Turns out there aren't that many things, and if you have this overview, it's not that difficult. Okay, things get more difficult when we hit chapter 4. And as I've said, we're going through chapter 3 as quickly as we can reasonably. Having missed today as a snow day, it'll be difficult to do that, but we're going to do our best. Okay. Curvature is another thing, okay? So if we're going to round a curve, okay, the curvature is just a property of the shape of the curve, okay? This curve has more curvature than this one, okay? Now, how do you define curvature? Well, the first thing we do is we define curvature in terms of what happens to the unit tangent vector, okay? If you're driving along and you go around a curve, your unit tangent vector is going to change, okay? The rate at which the unit tangent vector changes depends on how fast you're going. If you normalize that, so to speak, by dividing the rate at which your unit tangent vector changes by your speed, then you're going to get the same rate of change no matter what your speed is. If you're going twice as fast, your unit tangent vector is going to change twice as fast. Okay, but if you divide by the speed, you're going to get the same result whether you're going twice as fast or not. Think about it. If you're going twice as fast, you're going to have twice the rate of change of your unit tangent vector. Okay. So if you divide by your speed, you're going to get the rate at which your unit tangent vector changes just with respect to the distance you travel along the curve. Now, a little later, we'll talk about parameterizing a curve in terms of arc length. And we'll relate that result to what I'm talking about right here. But intuitively, what we're doing is we're taking our curvature, we're dividing the rate of change of our unit tangent vector, which is just the derivative of the unit tangent vector with respect to time. And we just do the magnitude of that because when we measure curvature, we're not measuring orientation. We're not measuring whether we're curving to the right or left. Okay, we can say we curve this much and we go around the curve in a counterclockwise sense and clockwise sense. And that's fine, but that's in addition. The sense in which we go around the curve is something that would be in addition to the curvature. Curvature doesn't care if you go this way or this way. Okay. So anyhow, there it is. We divide the rate at which the tangent vector is changing and divide that by how fast we're moving. There it is. And of course, there's a formula, you know, dt, well, the derivative of the unit tangent vector with respect to t divided by the magnitude of dr dt. Dr dt just being the velocity, your speed. If we divide by the magnitude of the velocity, which is the speed. Okay. So there it is. I did mention osculating circle over here. In class, I mentioned osculating circle and said I'd say a little bit about it. I told you that if we have a curve like this, the osculating circle is the circle that fits the curve best at a given point. And the osculating circle changes every time with every movement. The position, the center of the osculating circle is likely to change. The radius is likely to change. Okay? Now, the osculating circle or this curve would be something like this, would be a pretty big circle. Oscillate circle for a point right here in this curve would be a fairly small circle. So when we have the greater curvature, we have the smaller circle. Well, it turns out then that curvature, as we define it here, is just the reciprocal of the radius of our osculating circle. That's kind of a neat connection. This makes it fairly easy once you have your normal, tangent, and binormal vectors to figure out where the center of your osculating circle is going to be. We might do that later. It's really, I think, a pretty good exercise in visualizing some of what happens in 3 dimensions. And I think it's worth doing. We'll see if we can carve out time to do a pretty good explanation of that. Might be challenging. Certainly in your text, I'm not going to commit myself right now one way or another, whether it would be a legitimate thing to ask on a test. But we'll talk about it at least briefly. We've already done some. Okay, so we have all that, and that's a good part of the chapter. Now there is another topic. Is involved with arc length. Okay. Now you've already seen arc length for polar coordinates. Hopefully that invoked the formula you have for arc length for a function of one variable, the square root of 1 plus f prime squared integrated with respect to a variable. Okay, so I did have access to my chart. Okay, so anyhow, you got a function of 3 variables. Just an r of t equals x of ti plus y of tj plus z of tk. Your arc length increment, I'm just going to tell you, it's x prime squared plus y prime squared plus z prime squared. And it's probably written x prime of t plus y prime of t. Could be written dx dt quantity squared plus dy dt quantity squared. There are many ways to write it. I wrote it in the shortest possible form. And of course, we're also pressed for time in class and get as much in as we could, anticipating that we would be snowed out today. Okay. Anyhow, there's the arc length increment. What's that mean? That means the arc length from t equals a to t equals b is just the integral of that increment. So there it is. That's a formula for arc length if you know the x of t, y of t, and z of t functions. But why? Why is that? It's kind of important to understand that. It's also kind of important to understand that because, you know, I was talking about the 1 plus f prime squared integrated with respect to your variable. So when I wrote this down, I had a 1 there, a 1 plus. Okay, just strictly by analogy without thinking about why or what. And it was kind of fun because then I told you why it was this and found out that it was, or why it was this. Well, I worked out why it is what it is. And that's what we do right here. It's fairly simple to work out. And I got this, and there's no 1 in it. And I scratched my head, you know, what in the world's going on here? I just wrote that 1 out of analogy without thinking about why the formula is what it is. Then when I explained why the formula is what it is, I realized, boy, that was really a bonehead thing. I should have thought it through before I wrote it. Okay, it's not hard for me to think that through. I just didn't bother at the time. Take a lesson. Okay, don't do like I do. Now, there is the formula. That's how you get an arc length. The reason for that, if you got r of t, that's this flight vector here, and then r of t plus delta t, the position vector just a little bit later, okay, then you're going to be here. That'll be your yellow vector. Your average velocity between here and here is just the vector from the tip of the r of t vector to the tip of the r of t plus delta t vector divided by your time interval. Now, if we calculate v of t, and I didn't bother to write my primes there. V of t is x prime of t plus y prime of t, x prime of ti plus y prime of tj plus z prime of tk. Okay. If you actually calculate this at t, evaluate it at t, and multiply by your delta t, if your velocity is constant, then this blue vector that represents v of t delta t will go from the tip of the r of t vector to the tip of the r of t plus delta t vector. Now, if you look closely at my picture here, it should be clear that that blue vector is quite a bit longer than the distance from here to here. It goes beyond the tip of the yellow vector. Okay. And what that would mean is, in this case, things actually slow down. The distance that we move, or v of t delta t, is a distance we move as we would predict it based on our velocity at time t. If our velocity decreases, then we're not going to move as far, so that our r of t plus delta t will come up short of our r of t plus v of t delta t vector. Well, I'm going to have to repair a couple of smudges here. Do that pretty easily. Okay, so I say r of t plus delta t is approximately equal. Those are wave equal signs. It's not equal to r of t plus v of t delta t. But if t is small, we expect it's going to be very close. Okay. As t approaches zero, the difference between this and this approaches zero, assuming that this is a smooth function, a differentiable function, and continuous and all that stuff. What I've said then is that the difference between this side and this side is going to approach zero, in the sense that then the ratio of this to this will equal 1. Ratio of this over this approaches 1. Distance along our path during this interval then is approximately equal to, see if we can make it a little clearer again, got smudged. V of t delta t, that's really what I'm trying to establish with all this. Okay. If that's the distance we travel in time delta t, then since the magnitude of v of t is just this, because there's our v of t vector, we just add the squares of its components, take the square root. Then if I multiply this by delta t, I'm going to get something that pretty clearly gives us this increment in the limit as delta t approaches zero. Okay. In other words, this magnitude of v of t delta t will actually be equal That's the distance along the path, during the interval from t to p plus delta t. It's approximately equal to this, and in the limit, you can say that it gives you this infinitesimal quantity here, okay? This thing that we end with. Now, we could break this, we partition the interval from A to B and so form a Riemann sum, and we'll probably do that, okay? And I believe your text probably does that. And then prove it, using the standard technique when you let your delta t's all approach zero, you see that you do get this integral, okay? Okay, well, bottom line, there's your integral, and there's a good reason for it, and this is pretty much what the reason is. We can do it just a little more formally, but in a quick survey of a whole chapter and a one class survey of a whole chapter, what we did was waved our hands over a lot of things, and we'll continue to wave our hands over some things, but we'll do some other things a little more rigorously. Okay, so there it is. So I'll be posting this in conjunction with the original class, which much to my regret, lost about half its video. I'd be talking along and then I'd keep talking and there'd be no sound. Then the sound would come back and then it would go away. Haven't figured out why. I think it might be the microphone. Okay. There it is.